What is a thermonuclear bomb, and how does it work? In the comments under a video on our channel dedicated to conventional nuclear explosions, many viewers asked me to explain in more detail the physical principles behind thermonuclear weapons. And that is exactly what we are going to do in today's video. By the way, when I first started preparing the script, I honestly thought that I already knew everything I needed, and that the work would not take very long. Unfortunately, in reality, it turned out that there was a lot I did not know at all, and some things I had been confident about were not entirely correct. So I think that even for my respected viewers, who are already interested in the topic of nuclear and thermonuclear weapons, this video will contain something new and interesting. As follows from the name, a thermonuclear bomb derives its destructive energy from thermonuclear fusion reactions, that is, the fusion of light atomic nuclei into heavier ones. Such reactions are the source of energy for stars in nature. The conditions required for these reactions are extremely extreme, temperatures of hundreds of millions of degrees and pressures of billions of atmospheres. And although the idea of extracting energy from thermonuclear fusion, both for peaceful and military purposes, arose even earlier than the discovery of the forced fission reaction that gave rise to nuclear weapons and nuclear power. For a long time, it was impossible to implement these ideas in practice, simply because creating conditions similar to those in the core of a star under terrestrial conditions turned out to be extremely difficult. However, when the first nuclear explosions occurred, it became clear that in the centers of such explosions, for a very brief moment, exactly such conditions are created. This gave rise to the idea of using nuclear bombs based on fission reactions as a kind of detonator for thermonuclear bombs that use fusion reactions. Thus, the thermonuclear bomb moved from being an abstract idea to an engineering concept. And here it is probably the right moment to ask the question, why were thermonuclear bombs needed at all if the military already had nuclear ones? The answer is quite simple. Nuclear bombs did not seem terrifying enough in terms of their destructive power. More precisely, creating a nuclear bomb with a yield greater than about 500, 600 kilotons, or roughly half a megaton, turned out to be an almost impossible task for reasons rooted in some very interesting physics. The key concept in the physics of nuclear fission is the critical mass, the minimum amount of fissile material that must be present inside a nuclear device for a chain fission reaction to occur. Atomic nuclei that support such a reaction, such as uranium-235 or plutonium-239, when struck by a neutron, split into two or more fragments and several additional neutrons. These neutrons then initiate the fission of even more atoms, and so on. But for this to actually work, all or at least most of the neutrons released at each step of the reaction must find a target in the form of another nucleus, and this does not happen automatically. Atomic nuclei are extremely small and occupy something on the order of 10 to 15 of the total volume of matter. Most likely, a given neutron will simply miss a given nucleus and fail to initiate a reaction. By itself, this is not a problem. After missing one nucleus, a neutron may hit the next one, or the next, or some other one. Purely by probability theory, sooner or later, it will find a target, since there are an enormous number of atoms in matter, on the order of 10^24 per kilogram. The problem, however, is that this encounter may occur too late, or rather, not occur at all, before the neutron escapes beyond the boundaries of the fissile material. In that case, it is lost to the reaction. The rate at which neutrons are lost through the surface of a piece of fissile material is proportional to the area of that surface, that is, to the square of its linear size. Meanwhile, the rate at which neutrons are produced inside the material is determined by the number of atoms, that is, by the mass, the volume, and thus by the cube of the linear size. In other words, as the size and mass of the piece of material increase, the probability that a neutron born somewhere near the center will escape decreases, while the probability that it will find a target inside the material increases. This is a kind of nuclear version of the square-cube law. It is precisely this principle that underlies the concept of critical mass, the minimum mass of material required so that a sufficient number of neutrons remain inside and cause fission reactions. For pure uranium-235, for example, this corresponds to a sphere with a radius of at least about 8.7 centimeters, weighing roughly 52 kilos. These 52 kilo are a very approximate figure. For instance, if the uranium is shaped not as a sphere, but as a cube, which for the same volume and mass has a larger surface area, the critical mass increases. Conversely, if the uranium is compressed, increasing its density and reducing the distance between atomic nuclei, the critical mass decreases. One can also surround the fissile material with a substance like beryllium that reflects neutrons back inside rather than letting them escape, which can reduce the critical mass by a factor of 2 or 3. It is important to understand that critical mass is, as mathematicians would say, a necessary and sufficient condition for a chain reaction to occur. If the mass of fissile material is below critical, the reaction will not proceed, and any initiated reaction will die out. But if the critical mass is exceeded, the reaction will proceed inevitably without any additional effort on our part, even if we did not intend to start it at that moment. In the history of nuclear physics and nuclear energy, there have already been several cases where researchers accidentally created a supercritical amount of material during experiments, triggering a chain reaction and receiving lethal doses of neutron and gamma radiation. Such an accidental initiation of a chain reaction is definitely not what we want, including when we talk about a nuclear bomb. Inside the device, of course, there must be an amount of nuclear explosive material significantly exceeding the critical mass. But when the bomb is calmly sitting in an arsenal, waiting for its time, it must remain in a subcritical state. To achieve this, the fissile material inside the bomb is divided into subcritical portions that are geometrically separated from one another, and at the moment of detonation, they are rapidly brought together. In modern bombs, these subcritical portions are surrounded by a shell of conventional chemical explosives. When the bomb is detonated, these explosives are triggered. The resulting inward-directed shock wave compresses the fissile material, achieving supercriticality. And now, we have come very close to answering the question of why it is impossible to create a nuclear bomb of arbitrarily large yield. At first glance, it seems simple. Just put more uranium or plutonium into the bomb, and you will get a more powerful explosion. But it turns out that things are not so straightforward. A very large amount of nuclear explosive material must be divided into a very large number of small pieces in order to keep the bomb subcritical during storage. When these pieces begin to move closer together, even before they fully merge, a region near the center of the bomb already reaches criticality, and a chain reaction starts. Rapid energy release, heating, and then evaporation of the fissile material begin. As a result, only a small fraction of the material manages to react, while the rest simply scatters uselessly into the surroundings. And the more fissile material there is in the bomb, the smaller the fraction that manages to react. This is why the practical yield of a fission-based nuclear bomb is limited to about 500 kilotons. Thermonuclear reactions do not have this problem. They do not require a critical mass. No matter how much material we place under conditions where the reaction can occur, all of that material can, in principle, react. However, as often happens, there is a significant gap between theory and practice. The first problem is the reaction itself, the fusion of heavy hydrogen isotopes, deuterium with 1 neutron and tritium with 2 neutrons. The result is a helium-4 nucleus with 2 protons and 2 neutrons, while the extra neutron flies away. Both deuterium and tritium, like hydrogen itself, are gases and are highly volatile. A bomb containing a sufficient mass of these gases would be very large in size. One could, of course, liquefy these gases, but that would require cooling them down to about 25 Kelvin, or approximately 248 degrees Celsius. Such extreme cooling would require large and heavy refrigeration systems whose mass alone would reach tens of tons, clearly unsuitable for real weapons. The solution was found in the use of a hydride, more precisely, lithium deuteride. Lithium hydride is a solid at room temperature and pressure, making it much easier to handle. When lithium deuteride is placed in a potoke of neutrons, for example those emitted from the center of a nuclear explosion, the nuclei of lithium atoms absorb these neutrons and split into helium-4 and tritium. About 4.8 MeV of energy is released per reaction, which by itself enhances the explosive effect. But more importantly, tritium is produced, which under the conditions at the center of a nuclear explosion reacts with deuterium, releasing an additional 17.6 MeV of energy. The key question remains, how do we actually initiate a thermonuclear reaction in a deuterium-tritium mixture. Yes, at the epicenter of a nuclear explosion, temperatures and pressures sufficient to start such reactions are achieved. But the problem is that at the same time, the explosion disperses the material rather than compressing it, which is what we need. Historically, the first scheme capable of turning expansion into compression was developed in the USSR and was known as the RDS-6-ITS design, also called the Sakharov layer cake. The idea was as follows. Inside the device, there is a small nuclear charge with a yield of several tens of kilotons, surrounded by alternating layers of deuterium and natural uranium, consisting mainly of uranium-238. Uranium-238 does not support a chain fission reaction. More precisely, it can undergo fission under the action of neutrons, releasing 2 or 3 new neutrons, just like uranium-235. But this requires very high-energy neutrons, on the order of 10 MeV per neutron. Meanwhile, the neutrons produced during the fission of uranium-235 or uranium-238 itself have average energies of about 1 MeV. In other words, the neutrons released during fission cannot initiate further fission events in uranium-238. That is why a chain reaction does not occur in natural uranium, and shells made of this material can be of any mass without worrying about criticality. All of this is surrounded by a layer of conventional chemical explosives. Detonation begins with the explosion of this outer layer. The resulting shock wave compresses all the internal layers, causing the central nuclear charge to reach critical mass and initiate a chain reaction. Neutrons emitted from the surface of this charge cause lithium deuteride to transform into a mixture of deuterium and tritium. As it heats up, the nuclear charge material begins to expand, pushing the layers above it outward. But the key point is that the bomb is still being compressed from the outside by the shock wave generated by the chemical explosives. Under pressure from both outside and inside, a thermonuclear reaction occurs in the lithium deuteride layer, producing helium-4 and neutrons. And here is the most interesting part. These thermonuclear neutrons have much higher energy than the purely nuclear neutrons from the initial explosion, about 14 MeV. Such neutrons are fully capable of causing fission in uranium-238 in the uranium shells. Each such fission event releases about 200 MeV of energy, an order of magnitude more than the fusion reaction itself. This energy contributes to heating and expansion of the uranium shells, which in turn further heat and compress the deuterium-tritium layers, strengthening the thermonuclear reaction. Thus, the main source of energy in a thermonuclear explosion is actually not fusion, but still nuclear fission, specifically the fission of uranium-238 nuclei. But to start this fission, we first need high-energy fusion neutrons. And to get those, we need to initiate the thermonuclear fusion of deuterium and tritium, which in turn requires detonating the internal plutonium charge. The Sakharov layer cakes were the first thermonuclear bombs that could realistically be used as weapons. However, later, a more efficient scheme was recognized: the Ulam design. In this design, the primary nuclear charge, surrounded by a shell of chemical explosives, is placed at a distance from the thermonuclear or secondary stage, which is usually implemented as a cylinder. Inside the cylinder is a rod, typically made of plutonium-239, often called a spark plug. The mass of this rod is made slightly less than critical. Around it is placed a layer of lithium deuteride, and outside that, a shell of uranium-238. When the chemical explosives surrounding the primary charge are detonated, the primary reaches critical mass and initiates a chain reaction, producing a flux of neutrons as well as gamma and X-ray radiation. The materials of the primary are chosen so that most of this radiation energy is carried by photons with energies of about 11 keV, so-called soft X-rays. This X-ray radiation propagates from the primary charge, reflects off the walls of the casing, and falls onto the secondary charge, rapidly heating its surface to very high temperatures. The material of the outer casing of the secondary heats up and begins to evaporate. The evaporating atoms carry away momentum, and by conservation of momentum, the shell begins to compress. This process is called ablation. Ablation compresses the contents of the entire secondary assembly, much like the shock wave from the chemical explosives did in the layer cake design. To make the process more uniform, The space between the charges is often filled with light polymer materials, such as polystyrene or polyethylene. Under X-ray irradiation from the primary, this material heats up and turns into plasma, ensuring a more uniform compression of the secondary. Under ablation, the secondary deforms, losing its cylindrical shape and becoming more spherical. The same happens to the central plutonium spark plug, which leads to a reduction in its surface area. And as we discussed earlier, reducing the surface area reduces the critical mass. If before the explosion, the plutonium spark plug was subcritical, after ablation compression it becomes supercritical. A chain reaction ignites in the plutonium rod, which is no longer much of a rod at that point. Essentially, a second nuclear explosion occurs inside the secondary assembly. After that, the process is largely the same as in the layer cake design. Neutrons from the centers of both explosions convert lithium into helium and tritium. The heat of the second explosion heats the material. The expansion of the rapidly expanding spark plug, combined with the compression of the outer layers due to ablation, creates the required pressure. The fusion reaction of deuterium and tritium begins, producing high-energy fusion neutrons that initiate fission of uranium-238 in the outer shell. This shell heats up and expands even more, further heating and compressing the deuterium-tritium mixture. The fusion reaction intensifies, producing even more fusion neutrons per unit time. Even more uranium-238 nuclei undergo fission, releasing even more energy. An explosion occurs. The entire trick is to calculate the bomb's design, so that all these processes in the secondary stage occur before the shock wave from the primary nuclear explosion reaches it. Otherwise, the shock wave would simply destroy the secondary stage, and no thermonuclear explosion would take place. This is extremely difficult to achieve and requires very careful selection of the parameters of the initiating nuclear charge, the geometry of the internal cavity and all its parts, and the materials used. For these same reasons, a detailed description of all elements of thermonuclear bombs and a full explanation of all the physico-chemical processes occurring in them remain strictly classified. But these are technical details that do not concern us too much, since we are not actually going to build a thermonuclear bomb, and we would not be able to anyway. In principle, there are no fundamental limits on the yield of a thermonuclear bomb built according to the Teller-Ulam scheme. More than 90% of the energy of such bombs comes from materials that are passive in terms of nuclear reactions, such as lithium deuteride and uranium-238, which can be included in practically unlimited amounts. The fissile components, uranium-235 or plutonium, are needed only to initiate the reaction, and their mass can remain small even for extremely powerful bombs. Later, it became clear that not only extremely powerful bombs are more convenient to implement in thermonuclear rather than purely fission-based designs. Today, even warheads with yields of several hundred kilotons are often made thermonuclear. This is primarily because Teller-Ulam bombs are more predictable. Their yield can be calculated quite accurately, and it will be neither greater nor smaller than expected. In contrast, classic fission bombs depend heavily on the uniformity of compression of the fissile material by chemical explosives. Even the smallest construction defects can significantly reduce the bomb's yield, and in real physical devices, achieving 100% perfection is never possible. Even more interesting is the fact that thermonuclear bomb designs allow the creation of weapons in which certain destructive factors can be artificially enhanced while others are reduced. Such selective effect weapons are often called third-generation bombs, with first generation being pure fission bombs and second generation being the thermonuclear bombs described above. Third-generation bombs include, for example, neutron bombs, in which 81 or 90% of the explosion's energy is carried by neutron radiation, while the roles of other destructive factors are significantly reduced. Neutron radiation primarily affects living organisms and causes minimal damage to buildings and structures. Thus, by dropping a neutron bomb on an enemy, one can effectively kill or incapacitate the enemy while leaving material assets largely intact. Come in, take them, and use them. The details of real neutron bomb designs are extremely top secret. However, what we already know about the physics of thermonuclear explosions and physics in general may be enough to imagine, in very broad terms, how they might be constructed. The thermonuclear fusion reaction of deuterium and tritium itself already produces a powerful neutron flux. As we mentioned earlier, of the 17.6 MeV released in each such reaction, 14 MeV goes into the kinetic energy of neutrons. In second-generation bombs, this energy is used to initiate the fission of uranium-238, producing even more energy, mainly in the form of heat. But if the uranium shell is removed and replaced with another material that does not strongly absorb high-energy neutrons, such as lead or tungsten, one can obtain a bomb with lower overall yield but a much stronger neutron flux. The issue here is not only the number and energy of neutrons, but also the radius of destruction. In classic nuclear and thermonuclear bombs, the neutrons emitted typically have energies of a few MeV and travel only hundreds of meters in air before being absorbed. For high-energy neutrons with energies around 14 MeV, the effective radius of neutron damage increases to several kilometers. The effect can be further enhanced using so-called neutron multiplication methods. For example, the thermonuclear core can be surrounded by a shell of beryllium. Under the conditions at the center of a thermonuclear explosion, beryllium, specifically beryllium-9, can participate in two main nuclear reactions. First, it can efficiently absorb a neutron, and then transform into beryllium-8 while releasing two neutrons. This so-called N1-2N reaction effectively doubles the neutron flux. In addition, a beryllium-9 nucleus can absorb a helium-4 nucleus, which is produced in large quantities during fusion reactions, forming carbon-12 and releasing a neutron. Taken together, a beryllium layer can potentially triple the neutron flux passing through it. Once again, the details of neutron bomb designs are not available in open sources, but physics itself cannot be classified. So it is possible to make an educated guess about how all of this works, and I believe there is a solid degree of truth in this description. Thermonuclear bombs without uranium shells are also characterized by very low radioactive contamination of the terrain. Indeed, the main source of contamination in conventional bombs is fissile material, uranium and plutonium, and their fission products. Thermonuclear fusion produces stable helium as its reaction product. The only sources of contamination are the initiating nuclear charges and the plutonium spark plugs, whose mass remains very small even in powerful bombs. However, in second-generation bombs, most of the energy comes from uranium shells, which also produce significant radioactive contamination. But if avoiding contamination is critically important, even at the cost of reducing explosive yield, this approach may make sense. There is also the concept of bombs designed to produce a powerful electromagnetic pulse, so-called EMP bombs, which can be used to disable the enemy's electrical and electronic systems, communications, and so on. The idea of such weapons is widely discussed, but I could not find declassified data even confirming their existence, let alone their design. Nevertheless, we can still imagine how such bombs might work based on basic physical principles. However, we will talk about that in one of our future videos. Nuclear and thermonuclear weapons are terrible weapons of mass destruction, and arguably among the most frightening inventions ever created by humanity. But if we abstract away from their purpose, the physics underlying their operation is extremely fascinating, and the ingenuity of the engineers who brought physical laws to life is truly impressive. In our future videos, we will continue exploring how human ingenuity has managed to harness various natural phenomena. For example, I am already preparing a video on different types of nuclear reactors that use the same principles to produce the electrical energy we all rely on. And in another video, we will discuss possible designs of thermonuclear reactors, which I personally hope will eventually replace fission reactors in the foreseeable future. So if you are interested in atomic and nuclear physics and nuclear energy, be sure to subscribe to the channel so you don't miss anything interesting. And that's all for today. All the best, dear friends, and see you again soon in our next videos.